this section, we will cover two of the most common plots, the box plot and the simple plot. For the first exercise of this section, create a box plot that displays compression ratios results per technique from the file ratio.csv available in the data directory. The data represents measurements obtained for a number of data compression software. The CSV format corresponds to comma-separated values. It is used to store tabular data, which can be seen as a table, where each column corresponds to the results of a specific technique. The first row of the table is what we call the header of the table. It contains the name of each technique. We start by importing the CSV package to read the CSV file and set some useful variables. Note that we could set the labels by directly using the CSV file. We defined it here for convenience. Next, we need to read the data for each technique from the file into memory so that we can access data for a specific technique on demand. To do this, we will define a simple function called getColumn, which will take as input a file name and a column number with index going from 0 to n-1. We will use this function later. Using the data read by the CSV package, we will then create a list corresponding to each row for the requested column. Finally, we return the list. From there, we will create a sequence of vectors using our lists to conform with the boxplot function requirements. Once all of this is pre-processed, we are ready to generate our boxplot. The last step that we will do is to replace the TIX labels on the x-axis with the techniques names. And here is the result. The main difficulty here was to pre-process the data to conform with the function. We needed to use the CSV package and then read the data into a specific way. There are simpler ways. Here, we will now produce a similar plot using pandas. The readCSV function of pandas returns a data frame, which we will call df. We can use this data frame directly to create plots. In the present case, we will do it by typing df.boxplot, and then simply to create a plot similar to our previous example, we turn off the grid. And voila! We only have now typed a few lines of code to generate a similar plot from the previous example. Next, let's look at creating a multi-panel plot where each panel corresponds to the result of a specific experiment. To create a multi-panel plot, we need to use the subplots function. This function returns two variables. The first one is the figure, and the second one is an array where each element is a specific subplot. In the present case, we will generate a 2x2 plot. Each panel will be sharing the x and y axis, meaning that they will all have the same range of values. For cuteness, we will hide some ticks on the x and y axis to avoid overcrowding the plot. Next, we will do a similar job as in the previous example, with the difference that we will read the data from 4 different files, one per experiment, and plot each of them in a different quadrant using index variables x and y. And here's the multi-panel plot. Now, let's move to simple plots. We saw in the very first example how to create a plot, and we also used it when plotting the fit to the histogram. In the next example, we will see how to create a 1D plot representing spectral data taken from a spectral cube. Using the fits module of AstroPy, we first read the spectral cube into the cube variable. Following the fits format, a spectral cube can contain many different sections, which we call HDU. For this example, we are using a spectral cube from the Things survey, available online. This particular file contains a header that includes the metadata and the data itself. When loaded with AstroPy, we can access each of these by typing .header and .data, respectively. It is not rare for spectral cube data from radio astronomy to also include a fourth dimension about the Stoke. We will not use it here. Therefore, we set the first index to 0. Now, using a colon to say that we want all values in the spectral dimension, we also set the index for array and deck to the central pixel, as asked in the question. Having all of this, we can now plot the spectrum. To correctly depict what information is being plotted, we need to identify the range of values of the spectrum. We will need it to set the TIX values. So first, we start by saving the TIX labels. As FITS is a standard, it includes specific keywords in the header, in this case the primary HDU, to describe the data. We will use the following keywords to evaluate the spectrum values range. The keywords that we will use are related to the third axis, and so they are all finishing with 3 in this case. C-type 3, which is the type of the third axis related to wavelength or velocity. N-axis, the axis dimension. CR-val, the central velocity coordinate. CR-pix, which is the pixel coordinate at the reference point. C-delta, which is the increment value. And then B-unit, the unit value. We will use the following two equations to evaluate the x-min and x-max, corresponding to the minimum value of our range and the maximum of our range. We now plug this into our code and set an array of labels, where the number of bins here will be the number of values that will be displayed on our axis. And finally, we replace these TIX labels as well as the X and Y label using the actual units from the header. And here is our spectrum plotted with the right units. And this concludes this visualization tutorial.